Okay, so now we'll talk about the so-called full BFS, and also we're going to provide analysis of the BFS algorithm. So what we just said is that the breadth-first search, starting from a source node, will only visit all the nodes reachable from the source node S. So if your graph is disconnected, then this BFS would not visit all the nodes. It may not touch upon all the nodes, okay? But sometimes we want to be able to traverse the entire graph. We want to be able to touch upon every node, okay? But we can easily modify our BFS algorithm so that it can visit all the nodes. Well, how do we do that? Well, if you're watching offline, you can also think about this break and think about it for a second, okay? But essentially the idea is that, well, after I finish one round of BFS, I can now check and restart from a node which is not yet discovered. That means that it's not reachable from my previous source. And then I now restart BFS at that undiscovered node and then explore further. And I repeat till there's no undiscovered nodes left. Okay, till all the nodes are discovered. That's it. Okay, so that's the idea. And how do we, it may sound like that, do we have to run BFS too many times? And how do we really implement that? Okay, so we're going to see the modification of the algorithm. But note that in order, because we're now going to run the breadth-first search algorithm multiple times, okay? And also we need to maintain the status of the nodes because you cannot every time reset all the status to be undiscovered, okay? So we're just going to make a small modification. So this is the same breadth-first search algorithm before. Remember before we only take a graph and a source node as input, okay? So now we also take a new input, which is the status, the array status or hash table, okay? We pass status through the BFS. So, and if the status is not, it's not given, then you can initialize it to be undiscovered for everyone. So if this is not given, then we get the previous BFS back. But in general, we need to pass it. And how do we restart from an undiscovered node? And here's what we do. Okay, so this is what we call the full BFS. So you're going to run this to visit all nodes. Okay, so at the beginning, all the status are set to be undiscovered. Okay, and then we simply have a for loop. And if the status of a node is undiscovered, then I'm simply going to perform a BFS from that node as the source, okay? Now note that during this BFS, the status would change. So when we perform this BFS, many nodes here will not then be changed to be visited, okay? And then we continue to go through all the nodes. If any of them still left to be undiscovered, we will perform the BFS restarted at those undiscovered ones. Again, repeat till we finish exhaust the list of graph nodes at the end of it, because when we perform BFS at a node, we'll definitely change the status to be visited. So in the end, all the nodes will have a visited status. Okay, so that's the idea. That's it. Okay, so simply go through the list of graph nodes in a certain order, and then as long as the node is undiscovered, I run the BFS. And if a node is already discovered by previous BFS, okay, that means that the status is not undiscovered, then we will not call this, okay? All right, so to make this more clear, let's just use an example. Now, by convention, I should point out that by convention, in all the examples or in homeworks and so on, if the graph nodes are indexed by either numbers or alphabet, letters, and so on, we usually assume that the order is from small to large, okay? So if it's by letters, we think there's A, B, C, D, E. That's the order that we're in the graph, okay? So if a node has multiple neighbors, okay? Now we have to decide which one we're going to visit the first when we explore its neighbors, right? So we assume that we always explore them in this increasing order of either the letters or the numbers, okay? All right. So let me just put it a bit more clear that we assume this order, neighbors are explored in increasing order, either for numbers or alphabetically, okay? All right. Okay, so let's just look at one example. Now, at the beginning, so what we do is that we initialize our status. I'm going to draw this status array here. So this is our status. Okay, so I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I didn't need so long. Oops. Okay, so at the beginning, everyone was undiscovered. What does the algorithm do? The algorithm, remember, we have a for loop. We have a for loop, and for each node in order, we're going to check, okay? So at the beginning, we'll check the first node. So we're going to node 0, okay? And then we take node 0, and clearly right now the status is undiscovered. So, oops. So what we say is that, okay, we now run call BFS G 0, we start with source 0 and status. We pass on the status, right? So now we're going to call BFS at 0. What's the consequence of the BFS algorithm? Well, from there, we're going to visit all of the neighbor. So this is going to be changed to be visited, and in the end, we see that 2, 1, 2, 8, 4 are all going to be changed to be status visited. So this itself will be visited, 1 will be visited, 2 will be visited, and 4 and 8. So all of these nodes, after I perform BFS, starting from the source node 0, we're going to visit all of this, okay? So now the for loop will continue, okay? So the for loop just goes through this list, the nodes one by one. So the for loop now will go to the next. But this is already visited. So I don't need to run BFS starting from source node 1 anymore, okay? And then it go to 2, it's also visited, so nothing. And then when we go to 3, we notice that 3 is not yet visited. So now we're going to call BFS starting with source node 3 and pass on the status, okay? So where's 3? 3 now is here. So from 3, we find all of this other node, okay? That means that now, after I perform, after this BFS, starting from 3, I would have visited 3 and 5, 9, and 10. Okay, so this is not U, this is V. Okay, so now next we continue. The for loop continue. We were at 3, now continue to 4, but this is already visited, nothing. 5 already visited, we don't have to do anything. And then when we go to 6, we found another one which is not visited. So now we need to call BFS starting from 6 and pass on the status. So now we're going to do it here. From 6, we'll discover 7. And then from 7, we'll discover 11. So after this, 6 will be change status to be visited. 7 will change status, and 11 change status. Okay. Now, at this point, we don't yet know that we're already done with everybody because we don't know what to expect. We don't know the graph, right? So we continue and we go to 7, the for loop, visited, so nothing. 8, nothing. 9, we don't need to do anything. 10, 11, so on. And then we finish the processing, the entire list, and everybody in the end will be all visited. Okay, all right, so that's algorithm. Okay, questions? All right, so now note that, okay, what we see here is that even though that in the for loop, it looks like that we're going to have a for loop, which we're going to exhaust all the nodes in the graph, okay? But we only call this BFS one, the status of the current node is undiscovered, okay? And as we see in this example, what do I see? We only call BFS 3 times, okay? Once at 0, once at 3, once at 6. Okay, so we only need to call BFS 3 times in this example, which is the undirected graph. Okay, and this is not a coincidence. What happens is that in general, you're not going to call BFS at every node, because once you call BFS at one node in the connect components, you're going to then visit everybody else in that connect components. Okay, so then you don't need to call BFS at any other nodes within the same connect components as this source node. Okay, that basically means that in the end, the number of times that you're going to call BFS, okay, it's the same as the number of connect components in your undirected graph. Okay, is it clear? Okay, because if I call in each of the connect components, if I just run BFS once at any node, I'm going to reach all others, because what's the definition of connected components? It's basically from every node is reachable from every other node, right? So that means that starting from a node, I will be able to reach all others within this connect components. Okay, so you start with any node and run BFS, I would then touches upon everyone within this connect components. So that's what the BFS is doing. It's basically visit all the nodes that's reachable from the source. In the undirected graph case, that's the one in the same connect components of this node. Okay, so in summary, what I said is that if your graph, let's say assume it's an undirected graph, the algorithm of course works for both undirected and directed, but it's easier to state it for undirected graph. Okay, so if your undirected graph has k components, okay, then line 5 of your algorithm, this will not be called n times n's number of nodes. Okay, this will only be called exactly the same as the number of connect components you have in your input graph. Okay, so it'll be called k times. Like in the previous example, this is really we really get into this function only 3 times, once for each of the connect components. Okay. Okay. Now the same actually holds, because what happens is that the BFS only visits a node and everything it reaches. But then with directed graph, the concept of connect component is a bit tricky. That's why we don't make the statement, but the same idea holds there. Okay. All right, so now let's look at what is the time complexity of this algorithm. Okay, so in fact, it turned out that you will think in terms of the Full-BFS algorithm. Conceptually, it's actually a bit easier to see what the time complexity is. So we're going to actually start with the Full-BFS directly. Okay, because now what you'll see, we can use a global argument to count the operation needed, which first give us the time complexity of the algorithm. Okay, but note that the time complexity on the Full-BFS obviously will be an upper bound for the time complexity of BFS, because this time complexity will be smaller than or equal to this. Okay, so this will be an upper bound for the time complexity of BFS. Okay, all right. So here I put the entire algorithm on the same page. So this is a full procedure for performing BFS to visit all graph nodes. Okay, so have 2 procedures, a subroutine BFS, and the top level function is a Full-BFS. Okay, so as I said, if you just look at this algorithm, okay, on the surface, it's like, we have to call, potentially in the worst case, we could call this procedure n times. Okay, and then you may, if you go to each individual BFS and see how much time it's going to take, you may get to the conclusion that each individual one, worst case, can also take time, which is proportional to the number of nodes and the edges. Okay, then you'd think that now I have to blow that one up by a factor of v, because I have to potentially run this BFS v times. Okay, but this actually turned out to be not a tight bound. Okay, so the way, because we don't really know how many, it's hard to really see how many times we're going to call this procedure. So instead, we take a global view. Okay, we look into the code and we ask that where do I have to spend time? Which operations we have to spend time, and how many times do I have to run that operation? Okay, so in particular, the costly portion is this BFS procedure, right? So if you go inside, okay, so this all take constant time. because we assume that we're passing the status, okay? So here to set up the initial status, so let me actually clear this so that I can read, right? So to set up the initial status, this initialization, we have to basically set every node to be undiscovered, and that takes time linear to the number of nodes, okay? All right. So for this part, instead of saying, looking at the for loop, I'm going to take a global view. So within the BFS algorithm, this part, this is just a constant time. Okay, then we get into the while part. Now, the final time complexity depends on how many iterations. So what we really want is that we want to know what is the total number iterations of while loop across all the calls made in the for algorithm. Okay, so number one, I need to know how many iterations we're going to execute this part within the while loop. Okay, that's number one. Okay, number two, we look at within the while loop, how much time do we take? Well, this takes constant time. Okay, here we have yet another for loop. How many iterations within the for loop? That's constant time. Okay, but how many iterations does the for loop take? Well, for each node U, here I have to visit all its neighbors, right? So in other words, the entire for loop, I'm going to use a different color. The entire for loop actually takes time, which is proportional to, let me use some constant times the degree or the out degree, okay? So I'm using degree, but with the understanding that if it's direct graph, it should be out degree, okay? The degree of this node U here, okay? So, so this is what we have here, okay? So it's in the worst case, of course, the degree of a node can be large, but note that in general, instead of giving a bound directly, we're going to now accumulate the total cost, okay? So I'm going to write it on the next page because I don't have space here, okay? But what we have now is the following. I'm going to erase this part, okay? Okay, so what we have is that if you just look at this part, the total cost of while loop, okay? So I'm going to look at the total cost of all while loops. Okay, so I first give the intuition and then I'll go a little bit more formal. Okay, what's the intuition? We look at this the total cost of all the while loop. We notice that, okay, number one, the total number of times depends on that how many times we take some nodes come from the pending list, right? And if you think about it, every node in your graph can only get insert, their status can only change from undiscovered to pending exactly once, okay? Once it change to become pending, later you take it out in the while loop, and then you process and the change to be visited. You will not become pending again, okay? So every node had exact one, will be in the become pending exactly once, okay? So I'm going to write it here. So each node will be pending exactly once. Hence, each node will be processed in the while loop exactly once. Okay, so that's the first observation. Okay. The second observation is that, okay, when we process a node, okay, we're basically going to execute this part star. Okay, so this part called star. So we're basically going to execute this part star for every node exactly once. Okay, and when we process this node, how much time do we take? Well, we actually visit all its neighbors, right? In other words, we look at all the outgoing edges incident on this node U, right? Okay, now what that means is that the time that we need for each node, when we process it, we need time exactly proportional to the number of outgoing, depends on whether directed or not, edges incident on U, right? That's what we do, okay? Now, when you put them together, okay, so in other words, this cost here actually is proportional to the, for node U is proportional to the number of edges we're going to, is incident on U, okay? So when you take all of the nodes together, okay, how many times, now range over all nodes, which is basically when you consider, that is when you're considering all while loops ever called in DSC, okay? Now, every edge will be visited exactly once for directed graph and exactly twice for undirected graph. Why? Because if you consider each edge, right? For directed graph, we'll only touch this edge once. If you have edge UV, we'll only touch the once when we're exploring node U, okay? Because then through this edge, you go to V, okay? So you will only touch this edge once here, okay? While for undirected graph, for an edge, then we're going to touch it when we explore this graph neighbors, we're going to touch it twice, once for each of its endpoints. So when you have an edge UV in the undirected graph, when we're exploring U, we're going to visit the edge UV to find its neighbor V. And when we're going to exploring V, we're going to go through the edge VU to find its neighbor U. Okay, so you're going to touch it twice. Okay, so now putting all of this together, what do we have? What we have is that, so I'm going to remove this. So at the beginning, the initialization to set up the status take a V time. So putting all of this together, the time complexity for the entire BFS algorithm is V plus E. Why? Because by our previous argument, okay, this portion, the total cost for this portion, the total cost, so this is star, the total cost for the star part, okay, basically is proportional to the number of edges, because in this portion, we either, we'll get into the for loop is basically each time we come here, that means we're visiting through an edge UV. Okay, so this is proportional to the number of edges. So this gives us order of E, the total cost. Okay, and the beginning give us the order of V, and also here, just to get into the while loop, the total number of iteration of while loop is also V, because we're going to visit every node, because every node will be pending once. So total number of iteration of while loop is V. So the total time complexity is V plus E. Okay, so let me actually go a bit more precise. So the total cost of while loop, we said that we're going to visit the while loop. We're going to visit every node in your set once, right? Because each node, let me actually use U. Okay, because I mean, each node become pending exactly once. So we're going to visit in the while loop, we're going to visit every node exactly once, okay? And for each node U, what do I have to do? I have to spend a constant time here, and I also have to spend, this is the degree of U we set, okay? Some constant time that. So for each of the U within the while loop, I have to first spend some constant plus, this is for this line, okay, plus the total cost of the for loop, which is proportional to the degree of U. Okay, so let me annotate. This is the time for the for loop. So this is the start. Okay, and this is the total time you need to spend for, so this is the total time to process, to explore U. Okay, I visit all its neighbors. Okay, so what is the summation? Well, the summation now, okay, the summation is simply the sum of U in V times constant plus C prime U in V and the degree of U. The first term is proportional to the number of nodes. The second term, we said earlier, which is total sum of degree of all nodes in the graph, that's bounded by, that is basically E for direct graph or 2E for indirect graph. So this is proportional to E. So the whole thing as such is, okay, so this is the same as the intuitive argument that we basically count how many the edges appears. Each time an edge is visited, that's one where that's basically when we are in the for loop. Okay, so use this global argument, but you can also use this. This is a bit more formal analysis to see the total cost of the while loop. Essentially, is that in the while loop you're going to visit every node exactly once, and then within each, when you explore a node, you need to look at the node itself and explore its neighbor. So that's the cost you need to explore a node U. And the total cost is that the cost of exploring all nodes, which essentially give us this V plus E. Okay, so this is a bit more precise argument. Okay, all right. So this is the time complexity for the four breadth first search. Okay, and note that different from before, here I have to write both V and E. Why? Because for a given input graph, I have two types of variables. I have both the graph nodes and the edges. And as we mentioned before, when you give me the graph, I have no idea which one is bigger. I don't know whether V is bigger or E is bigger. In other words, I don't know who is dominating. Okay, all we know is that E is at most V squared. Sorry, E is at most the V squared. That's all we know. The number of edges at most, the number of nodes squared. Okay. So, but we don't know, but the E can be very small. Can be 0, can be linear, and so on. Okay. So if V is smaller than E, then this time becomes the number of edges will dominate, just become order of E. Or if V is bigger than E, then this become order of V. But since we don't know who's bigger, we have to write both. Okay. All right. Okay. Note that this time complexity, in some sense, so in what we just said is that the Full-BFS algorithm, it visits all the graph nodes in time order of V plus E. Okay, and note that as a graph search strategy, as a graph traversal strategy, this time complexity is optimal. Why? Because your graph size of the graph is V plus E. Okay, so even if you just look at each one in your write it into your computer to represent it, that takes this much time. Okay, so asymptotically, this time complexity is the best you can hope for visiting graph. Because if it's smaller than that, it means that there's certain edges or certain nodes you didn't visit. Okay, all right. Now what we just said is for the full BFS. Okay, but for individual for the BFS starting from a source node S, then it's very easy to see that using the same argument, the time complexity that we need is actually V plus MS, which is the number of edges in the component, in the connect components of G connecting S. Or for direct graph, this is the, so this is for undirected graph. Or for direct graph, MS is the number of edges spanned. It's a bit more complicated, spanned by nodes S plus or nodes reachable from S. Okay, so it's a little bit complicated to state. That's why we tend to not to say it for, but roughly speaking, if it's undirected, then you only need to, because you are only visiting that connected components. So you only need to visit all the edges in that connected components. So the time complexity, if that connected component is small, you don't need to visit the other nodes outside of that. Okay, so this is the time complexity. V comes from, because at the beginning, you don't know, you have to set a status for every node, so that already takes times V. Okay, so, but nevertheless, it's very easy to see that this clearly is bounded by, because this is smaller than E. Okay, so that's it's clearly bounded by the time complexity of the full BFS.